In this video, we're continuing our exploration of section 1.2, and our objective is to distinguish between different families of algebraic functions. These are functions that we've encountered in the past, but we're going to be talking about them in a very broad setting, and our ultimate goal is to be able to use these effectively in our study of calculus. So, to overview, what is a family of functions? What we're talking about is functions that share key characteristics. And that can be determined from maybe one dominant feature or the way that it's defined algebraically. So first of all, we have to distinguish between what we call algebraic and transcendental. So we have two families of functions. We're not going to talk about the relative size of how many there are. I mean, we're talking about infinitely many. But algebraic functions can be described using algebraic operations. We're talking about your standard 4 binary operations, square roots, raising something to a power, nth roots, absolute value, and the transcendental functions, on the other hand, are not algebraic, and these include such things as the trig functions, the exponential functions, the logarithmic functions, and the hyperbolic functions. So these we'll explore in some detail in this chapter. The hyperbolic functions we're not going to get to until chapter 3. So first, what we're going to talk about is the different kinds of algebraic functions. And what we're going to focus on, so keep an eye out for, the essential shape of the graph. What would you predict that graph to look like if you know what the function is like? The function statements, so how do you recognize when that function is part of a family? And other things include things that we've discussed in the previous videos, including domain and range, symmetry / parity, monotonicity, and what sets them apart from others, right? So what makes them unique? All right, so let's dive in. The first class of functions that we're going to discuss here are what we call the power functions. The power functions have the general form f of x equals x raised to the n power, where n is some number that's not equal to 0. So we have a few different cases. For instance, if we have a positive integer remember that integer means it's a counting number, so whole numbers, discrete. And the graphs will look something like this. I'm going to draw the quintessential first. So here is y equals x. So x to the 1 power is a power function. And then we also have y to the x cubed. I'm going to label a couple of points here that are interesting for us to look out for. And we also have, let's do a couple more. Let's go orange. This one is going to be y equals x to the fifth. And we could keep going in this way, and eventually we'll find some very extreme looking power functions. So these are all, you may have guessed the pattern now. If n is an odd integer, in other words, if we can write n as 2k plus 1 for k being 0, 1, 2, etc. Right? So these are interchangeable concepts, right? That n is odd and that n has this expression. Then you'll notice a few things that are interesting, right? So these graphs all pass through the points 1, 1, and -1, -1. We have unrestricted domain. And range. You can get any number you want as an x value and any number you want as a y value. Also interesting to note, n is odd, and these are odd functions. That is, they exhibit symmetry about the origin. And some key characteristics, so what sets them apart when n is odd, is that they flatten out near the origin, but always increasing. And you can see that as we progressively constructed higher and higher powers for x that were still odd. Contrast that now with don't mind that, sorry. I'm again going to label 2 points. And here we're going to be talking about power functions that have even powers. So here we have y equals x squared. And next I'll do y equals x to the fourth. And let's do one more. Okay, we'll do a couple more. Here's a more intense blue. So that's y equals x to the sixth. And you can guess what the next one's going to look like. All right, we're going back to purple here. As you get successive higher powers on x that are still even. So remember, that's the difference now. So now n is even, and that means interchangeably we can write n as a multiple of 2 for any k equal to 0, 1, 2, etc. So that's the quintessential expression for odd and even integers that are positive. And you'll notice again some things that are true for both. So I'm going to highlight the ones that are true for both. Unrestricted domain and range. Sorry, that's not right. Unrestricted domain. On the other hand, the range for, so I'm going to write down here, the range for such a function that has even power is always going to be 0 to infinity unless we modify it somehow. These are now even functions, you'll notice because they're mirrored across the y-axis, so they exhibit symmetry across the y-axis. And they do flatten out near 0, 0, but they're not always increasing. So in one half of its domain, it is increasing, and in the other half it's decreasing. So that's the first case. Let's label these. Let's call this case 1. Case 2, if we have negative integer powers, we're talking about different kinds of functions, okay? Because the general form now, if we want to talk about it in terms of n is now negative, it might make more sense to think about it as f of x equals x to the n really being some 1 over x to the m, where m is positive and m equals negative 1. So the labels don't matter, but our point here is that we're actually thinking now about something that is fundamentally rational, okay? So let's graph a few examples. I'm going to make this one a little bit bigger. Some important points that they pass through include 1, 1, negative 1, 1, and negative 1, negative 1. So for instance, let's talk about 1 over x. So 1 over x looks like on the right side. And on the left side, we have, so they're mirrored across the origin. This is an odd function. All right. Now we'll do 1 over x squared. So that actually will look like y equals 1 over x squared. And we can keep going. For instance, we could do 1 over x cubed. All right, so we could do this all day, but we're not going to. So some key characteristics here, for instance, n being odd means, again, f is odd. And similarly, n being even means that f is even. They all feature, so of these functions, the negative integer power n, a vertical asymptote, y equals 0, and a horizontal asymptote. So what we mean by that is these are lines that the function gets close to but does not actually cross. So you'll see those, of course, quite a bit in this course, and you've seen them before in the past. So that's our horizontal asymptote, and this is our vertical asymptote. And they may or may not cross sometimes, but in this case, they never cross those lines. Okay, let's keep it moving. Our third case here for the power functions are what we call the fractional powers. So we're talking in this case about something like n equals 1 over k for k an integer. Well, we'll stick to positive integer. All right, so even here we have subcases, but we'll draw them on the same axis. So when we talk about fractional powers, remember that this actually really means we have root functions. So roots. All right, some important points to label here include 1, 1, and -1, -1. All right, so the first one is trivial because 1 over 1 doesn't matter. It reduces to 1, and that's not interesting. However, 1 over 2, so remember that these are, you want to think of these as f of x equal to kth root of x, but that's the same thing as x to the 1 over k. Our first one then, so I'm going to start from the cool colors this time. So x to the 1/2 is our square root function. Notice that it starts at the origin. It does not have a left half. However, x to the cube to the third, or yeah, 1/3 power does. So it looks more like this. So that's y equals cube root of x. And that passes the origin and has a left side. We'll keep moving. So what do we predict for 4th root of x? Well, then again, this only has a right branch. And let's do one more. Let's do y equals 5th root of x, just so that we have a nice complete. That should look like this. Oh, whoops, it's going to pass through that point too. Ignore that branch. But it does flatten out there. Okay, gotta erase that part now. No! Okay, whoopsie. So the one I want to redraw is this one. Okay, that's better. All right, so key observations then. When we have even roots. So k is a even number. We notice that the domain and the range are both 0 to infinity, including 0. We'll notice that also these are increasing on their whole domain. And what else? Well, they're unbounded. We know that because the range goes from 0 to infinity. Okay, so that's good. And they pass through the point 1, 1. Not terribly interesting, but odd roots. So the interesting part now is thinking about what do they share in common and what's different. Odd roots, remember, they have a domain that's unrestricted. So all real numbers. And so is the range. They are also, however, increasing on their entire domain. And one odd bit about writing odd roots, and this may be more helpful if you're trying to use Desmos, for instance. You may need to write, oops, that's not a K. You may need to write K kth root of x as a piecewise function where you explicitly define the right half in terms of what it's defined as, so x raised to the 1 over k power. But the left half is weird. You have to kind of account for the fact that it's going to be negative, a negative argument inside the radical. So you have negative x absolute value 1 over k, and then make that negative. Yeah, it's a lot. Again, this is not something that you necessarily need to know unless you are explicitly trying to obtain a graph of an odd root function and it's not giving you the left half of the function. All right, so those are all the power functions. And to finish off this video, we'll talk about polynomial functions. So let's talk about the polynomial functions now. So we've encountered polynomial functions just like power functions in our earlier studies. And remember that the general form is something along the lines of capital P of x equals a sub n x raised to the n power plus a sub n minus 1 x raised to the n minus 1 power all the way down to a sub 1 x plus a sub 0. So importantly, let's identify the pieces here. This right here is our leading coefficient. It's the number, real number, directly in front of the highest power on x. The highest power being called the degree. Each part of this polynomial function is called a term with corresponding power. And so we call this the linear term, a1x, and this is the constant term. Not all of them need to be present, just some of them. And all the coefficients are fixed real numbers, right? So what polynomial functions look like depends on the subfamilies. Yes, so you can have a family of functions and then you can have a subfamily. All of these do, ultimately. So let's talk about the subfamilies. So the first one is the constant functions. In other words, P of x looks like a sub 0. That one's boring. It's a straight line across the horizontal, and it's located at a sub 0. So a sub 0 is the height of this function, and it's not very interesting. However, the next case, which is the linear functions, we actually have discussed quite a bit. So we talk about them in excruciating detail in algebra. So P of x equals a sub 1x plus a sub 0. And you may recognize this more easily as mx plus b. So remember, what we're talking about here is the slope of the line that is defined. The line represents the graph of the function. And this is the location of the y-intercept. So we've talked about these before, but let's go ahead and graph them. So I'm going to graph a few example linear functions. 1, 2, 3. 1, 2, 3. Linear functions are special for many, many reasons. one of which we'll explore later in this class. But for instance, we have the quintessential. Let's go ahead and do, let's start with the hot colors. So we've got one of the power functions, p of x equals x, so 1x plus 0. We also have something like this linear function, which is p of x equals negative 2x plus 1. So the slope is negative 2. And the y-intercept is 0, 1. Okay, let's do one more. This line here is the graph of p of x equals 1/3 x minus 1. So that slope is positive, it's fractional, and the y-intercept is 0, negative 1. All right, so some key observations here. The slope, which is a1, determines whether the function is increasing or decreasing. Namely, if it's positive, it's increasing. If it's negative, it's decreasing. The y-intercept, on the other hand, is determined by a0. So, in other words, we have the y-intercept. We pass through the point 0, comma a0. And we can also solve for an x-intercept, if it exists. So, y-intercept and the x-intercept is negative a0 over 1, comma 0. Most of these lines do cross the x-axis and the y-axis exactly once. Sometimes, though, they can cross only once. Although they absolutely have to cross the y-axis once because it's a function. And then we can talk about quadratic functions. This is slow going, I understand that. But we want to be able to think about these functions in terms of a broader set of principles. So quadratic functions we'll call p of x equals a sub 2 x squared plus a sub 1x plus a sub 0. And of course, we commonly know this better as ax squared plus bx plus c. All right. Again, we'll graph a few representative quadratic functions, just a few. Oh, I didn't want to do that. Whoopsie. Okay. So we have our, let's use yellow first. And I'll set up the axes first. So we have y equals x squared, which is, again, it's a power function. We also have something like whoops. This parabola, which is can be written as y equals x plus 1 squared minus 1 with a constant in front, which is 1/2. And what this does is, this is actually an alternative way of writing a quadratic function. And it's an easier way to get it from the graph itself. But of course, if you expand it out, it should look like 1/2 x squared. And then there's a 2x term, but that's multiplied by 1/2, so that's plus x. And then there's a plus 1/2 term minus 1, so that's a minus 1/2. Right. So, that said, these can look like any number of essential shapes. So here's another one. And that one is y equals negative 3x squared. All right, enough about that. So what common characteristics do we have for quadratic functions? We know that we have up to 2 real roots, so where it crosses the x-axis. It does not necessarily have 2, but it can have up to 2. The leading coefficient tells us whether the function opens up or down. So you'll see the quintessential parabola shape. And if the sign in front is negative, then it opens down, and if it's positive, it opens up. And lastly, every parabola, and hence every quadratic function, has a turning point. So where it changes from increasing to decreasing, or vice versa, which is explicitly given by x equals negative a1 over 2a2. You may recognize that as the algebra formula, x equals negative b over 2a, and it's the location of the vertex, which is what we call the turning point. All right, so lastly, let's talk about general properties. So, general polynomial properties. These functions are incredibly diverse, but we have some commonalities. So first of all, we get up to, possibly all, but not necessarily, up to n roots, n x-intercepts, by the fundamental theorem of algebra. That's powerful stuff. We have up to n minus 1 turning points. So a linear function has no turning points, a quadratic function has 1 turning point, and beyond that, you can have up to 2 or 3 turning points, depending on the degree of the function. The end behavior, this is an important word. The end behavior, which means what happens when x is very large. And that can mean extremely negative or extremely positive. Is unbounded, it's infinite. So these functions shoot up forever or shoot down forever. And, very helpful, can always be written as a product of linear and quadratic vectors. And it's often more helpful to write it that way because it helps you graph it or understand the graph much more quickly. So let's do an example. So we're going to sketch the graph of y equals negative x squared times x minus 2. Okay, so we know that this is a polynomial function because it's a product of linear and quadratic factors. Okay, we can write it out more easily as if we distribute that x squared, we have negative x cubed plus 2x squared. And what that might be helpful for is for telling us what the degree of this polynomial is, which is degree 3. And so all the general properties, so up to 3 roots, up to 2 turning points, are in play here. And notice that the leading coefficient is negative. That'll be important as well. Okay, so how do we actually sketch this graph? What we can do is we can find a few important points, right? So we can find the y-intercept and the x-intercepts. It's possible there's more than one, right? So first of all, the y-intercept. That means plug in 0 and find what the y value must be. So y equals negative 0 squared times 0 minus 2 is 0. So the y-intercept actually happens to be also an x-intercept. It passes through the origin. 0, 0. As for the x-intercepts, we set y equal to 0 and solve for x. And here, having it in the factored form is much more helpful. So now we know by the zero factor property that x equals 0, or x minus 2 equals 0, which means x equals 2. And we already knew x equals 0 because we were given that was the y-intercept, and so now we also have it as an x-intercept. So we have fundamentally 2 points here that we want to examine. And so that's our lead so far. The next thing we can do is we can think about the multiplicity on the power, so on each x-intercept. So because x equals 0 is multiplicity 2, that's an even multiplicity, that means that's not going to define a straight through passing point. So an aside here that's important. So multiplicity, if it's odd, so in the case of x minus 2, that's a power of 1, then where it crosses the x-axis, the function is just going to go straight through. So if you zoom in, it looks like that. If it's even, what tends to happen then is the function bounces off. So it touches that point and then it bounces off. So locally, it kind of looks like a parabola if you zoom in. All right, now let's use that to our advantage. So remember, we want to find the graph of, we want to find the graph of this polynomial function. 1, 2, 3, 1, 2, 1, negative 2, 1, negative 2, negative 3. Okay, so we know it passes through the points 0, 0, and we know it passes through the point 2, 0. Now, at 0, remember that it bounces off. So it'll either look like this, or it'll look like this. How do we know which one is which? Well, what we can do, oh boy, what we can do is we can find another test point. So let's plug in -1. So y, when you plug in -1, gives you -1 squared times -1 minus 2, which is -1 times -3, which is positive. It's positive 3. What that means then is that our function starts off like this. And then it hits the origin, bounces up, comes back down, comes back up, and then dips down again at a turning point, and then crosses through x equals 0. To find the exact turning point, that requires calculus. Or we can use Desmos, and we can estimate the turning point that way. All right, so that's our sketch of the graph. This is y equal to -x squared times x minus 2. And in later videos, we're going to be exploring some more functions that are a little bit more exciting.